Hi there, and welcome to another video for the course of algorithm design. This is one of several videos in which I will be solving the same dynamic programming problem, it's the one that is currently on the screen, using several different methods. In this one, we're going to work backwards in 3D, whatever that means. But before I show you the solution, if this is the first video in this series that you are watching, please pause the video first and try to really solve the question yourself first. Much more valuable exercises like this if you really try and solve them yourself before you watch someone else solve them. So, if you still need to, pause the video now before I spoil the answer. All right. So, what have we got here? We need to write an n-line poem about m events. The events need to be treated in order. Each line should describe an event. And an event may be described by no more than k lines, but by at least one. So what do? Well, what I always try to think about is, okay, I have n lines, m events, but what really makes one problem? Or what really makes an instance of the problem special, right? So imagine at the start I have 100 lines, 50 events. Then the first question I will ask is, what should line 100 be about? And in this case, the answer is, well, it has to be about event 50. It has to be about the last event. But then, what are my choices for line 99? Well, either line 99 is also going to be about the 50th event, or it's going to be about the 49th event. Those are my choices. And then at some point, we still need to factor in the fact that we can have at most k lines for each event. But for me, I really like to break it down to what choice do I have? And as I outlined it just now, basically anytime I go to the next line, or now I suppose the previous line, I get to choose, do I want to switch event or stay with the same event? And this is what I'm going to try and cover, going to try and describe mathematically in our opt function. So our opt function is going to need to contain the choice to stay with this event or to change the event. Again, when I go to line 99, I can choose either I also have line 99 be about number 50, about event 50, or I have line 99 be about event 49. Those are my choices. Now, that means that what event am I talking about should probably be one of the parameters of my opt function. Similarly, what line am I talking about should also be one of the parameters. So let's have these two parameters. We'll call them I and j. I is for the current line, and j is for the current event. All right. And now we can already describe a little bit what's happening here. Because regardless of which we choose, we must go to the next line. And either we stay with the same event, or we also change the event. And since I'm reasoning backwards here, right, we start with 100 lines, 50 events. We go to line 99, and either we stay with event 50 or we go to event 49. We're reasoning backwards. This is very common in dynamic programming approaches. Okay. Now I haven't closed these parentheses yet. That's for a reason, but we'll worry about that reason later. But what else is going on? Well, the current line, I am going to assign to the current event. So we're going to add EIJ to this. The emotional score we get for inline I talking about event J. And we want to maximize our emotional value. So we're going to add the maximum of these two options. Okay. Now, this is all very nice, but what happens when at some point I will become 0 or j will become 0? What should we do then? Well, let's think about it. First, let's think about the case where I is 0 and j is also 0. In this case, we have no lines left, and we also have no events left. Okay, well, in that case, there's nothing else we can do. No more value to be gained. What about the scenario where I is 0, but j is not yet 0? Well, in that scenario, I have no lines left, but there are still events left. That's potentially very problematic, because each event needs at least one line on it. So this is a situation we would like to avoid at all costs. And if it is a situation we would like to avoid at all costs, in a maximization problem, we should make sure that it returns the thing we never want, minus infinity. The thing we will never be able to recover from. However much I add to this, it will never change. It will always remain minus infinity. So this is the biggest punishment or penalty we could give. And what about when j equals 0 and I is bigger than 0? In other words, we have no events left, but there are still lines left. Well, in that case, we also have a problem, because each line should describe an event. In other words, this is another scenario we would like to avoid at all costs. So in this case, we should also return infinity. Infinity, rather. Right? The maximum possible punishment for a maximization problem. Okay. Now there's just one more issue to deal with. It's this at most k lines per event. Because in order to keep track of that here, well, we also need to keep track of how many lines can we still spend on this current event. Or, equivalently, how many lines have we already spent on this event. And for that, we're going to need a third parameter. There is a third thing that we need to know about. Now, normally, I would call it ij and then k, but since k already has something here, and in my handwriting, the difference between a lowercase k and an uppercase k is very hard to see, I am instead going to call it alpha, just so that it is clear that there is a difference between capital K and lowercase k. We don't have to deal with it. I'm just going to call it alpha. And alpha is the number of lines we may still write about event j. Okay, so first let's see what happens here in our opt calls. If we stay with this event, then the number of lines we may still talk about this event simply goes down by 1. After all, we've just spent one more line talking about this event. We don't change this event, so there is one less that we can talk about. One line less that we can talk about it in lovely sentences. If, however, we change the event, well, then we basically have a clean slate again. If we change to the next event, then currently 0 lines are about that event, so we can still have another k lines talking about that event. And now there is one more thing to keep track of. Because what if we cannot stay with this event? What do I mean? Well, imagine that alpha is 0, that the number of lines we may still write about j is 0. We can spend no more lines talking about this event. In that case, we don't actually have a choice. We are forced to change the event. So we can do two things. We can do what is typical for what we saw in the knapsack problem, is that we add another case. And in this case, we say, okay, we don't have a choice. We must move on to the next event if alpha is 0. That's fine. That's one way to make this work. The alternative, or one of many alternatives, is rather than adding this extra case, which again is totally fine, totally correct, time complexity-wise, doesn't change anything about what I'm going to propose next. But one possible alternative is to instead utilize the fact that we already have this base case that assigns this maximum penalty. Because another situation we want to avoid at all costs is if alpha becomes negative. If alpha is ever negative, then we've spent too many lines writing about a certain event. In other words, this is a situation we would like to avoid at all costs. So, if alpha ever becomes negative, we should return the maximum penalty minus infinity to make sure this never becomes the solution we go for. Of course, now, in the first case, we also need to make sure that alpha is not negative. So rather than adding the extra base case for when alpha is 0, we can also handle it like this. Both are totally fine. Both are still backward solutions in 3D. Why 3D? Well, because we have 3 parameters here. So this will be a 3-dimensional matrix if we actually implement it iteratively. And there we go. That's one way to solve this problem. In another video, I will look at a forward solution in 3D. And in yet another video, I will look at the solution in 2D with the same time complexity. Hopefully this shows at least one way to solve the problem, but if this one doesn't make a lot of sense to you still, check out the other ones. Maybe one of the other methods is more intuitive to you. It's totally fine with me. There are many ways to solve a problem like this. Pick whichever way works best for you. Hopefully this video was somewhat helpful. I'll see you around in the next one. For now.